Welcome, curious minds, to the deep dive. Today, we're plunging into a world where, well, prediction models are everywhere. And yet, as a brilliant Leo Bryman once observed in this quote, it really resonates with me. Nowhere is it written on a stone tablet what kind of models should be used to solve problems involving data. That powerful idea really sets the stage for our mission today. We want to demystify some of these modern nonlinear regression methods. We're focusing specifically on tree-based models and neural networks. We're talking about the really powerful tools used to predict outcomes and why understanding them is, well, just so crucial, whether you're prepping for a big meeting or just want to be truly informed about data science these days.
Exactly. Our goal here is to, cut through some of that complexity. We want to deliver the core insights, maybe along with some surprising facts, about how these advanced methods actually work and why they matter for you as you navigate this world just full of data.
Okay, so let's unpack this. At the very heart of predictive modeling, the ultimate goal really is to predict an outcome, let's call it Y, using some raw data, Z. And the theoretical best prediction rule for this, under square laws anyway, is something called the conditional expectation function, or CEF. We can write that as GZ.
Right. Think of GZ as the true, often really intricate underlying relationship, between your data and what you're actually trying to predict. Now, traditional methods, things like simple linear regression or maybe lasso, they try to approximate this. They're fundamental, for sure. But sometimes they just don't have enough flexibility to capture, the true nuanced patterns in the data. They're basically trying to draw straight lines through a really curvy world.
And that's where we hit a wall, right? Because for really complex relationships, and maybe especially when we're digging into something like, say, causal inference, those straight lines often just don't cut it. Fully nonlinear strategies become absolutely crucial. We need them to accurately approximate that GZ. We need that flexibility to really see what's going on.
Precisely. We've got to go beyond those simple straight lines, those fixed curves, to capture the subtle ways variables interact and influence an outcome. So today, we're really focusing on the big players in this nonlinear space. Regression trees, random forests, boosted trees, and of course neural networks, including what we now call deep learning. These are the tools that let us get much, much closer to that ideal GZ.
All right, let's start with something maybe more intuitive. The tree-based methods. Regression trees, what are they, fundamentally?
Okay, so at their core, regression trees are kind of like a sophisticated sorting system. They work by partitioning your data space, where all your Z's values live, into a set of simple, distinct rectangles or boxes. And then within each of those boxes, you get just one single constant prediction. You can also imagine it as a series of nested if-then-else statements that just carve up your data and assign a specific outcome to each final group.
That makes sense intuitively. But how do they figure out where to draw the lines? How do they make those boxes in a smart way?
That's the clever part. It's all done through something called recursive binary partitioning. Imagine you're playing a really sophisticated game of 20 questions with your data. At each step, the tree intelligently asks the best possible yes-no question. It picks the optimal variable and the best split point to divide the data into groups that are increasingly pure, minimizing the prediction error as it goes. And the beauty of it is, this process automatically handles complex interactions and nonlinearities in your data. You, the user, don't have to explicitly tell it what interactions to look for.
Could you walk us through an example, maybe predicting wages like you mentioned?
Absolutely. Let's say you're trying to predict log hourly wages. You've got data on things like experience, education, maybe geography. A simple, say, depth 2 regression tree might first split based on whether someone has a college degree. So if college 0.5, meaning no college degree, it then might look at experience. If expert 14, perhaps the predicted wage is, say, $12 an hour. But if college 1 and expergal is 9.5, maybe the prediction jumps to $24. The tree just keeps finding the best variable and the best cutoff point at each stage to optimize those predictions.
Okay, so they sound pretty intuitive and understand, which seems like a big plus, especially for explaining results to people.
They are, yeah. Which is great for exploration, for explainable analytics. However, a single tree on its own can be a bit of a crude approximation, especially if the true relationship is smooth. And if you let them grow really deep, they can get quite noisy, because you end up with fewer and fewer observations to estimate the prediction in those tiny terminal nodes at the bottom. It's kind of like trying to draw a really detailed picture, but only having a really thick crayon.
Right. Is that where pruning comes in? To sort of sharpen that crayon?
Precisely. Pruning is a really crucial step to improve the predictive performance. It involves cutting back the branches of the tree, often guided by cross-validation, to stop it from becoming overly complex and just fitting the noise in the training data. So for you, the practitioner, this means finding that sweet spot, that right balance between complexity and generalizability. You want to make sure your model works well on new data, not just the data you trained it on.
But if single trees can be a bit crude, what's their main weakness? And how do we get more power from this tree idea? I keep hearing random forests mentioned as the solution.
You're right. Single trees, like we said, can struggle with smooth functions, and they can be pretty unstable. Small changes in the data can lead to a very different tree structure. And that's exactly where Leo Breiman's brilliant idea of random forests comes in. The key insight here, maybe for your next data challenge, is this. Random forests work because they harness the wisdom of the crowd. The core idea is to build many different deep trees. Individually, these deep trees might have low approximation error but might be noisy. And then you simply average the prediction rules across all of those trees.
Averaging them. Okay, that sounds like it would smooth things out, make them more robust.
Yeah.
But how do you get many different deep trees from the same data to average in the first place?
That's the bagging part, which stands for bootstrap aggregation. Each individual tree in the forest isn't grown on the entire data set. Instead, it's grown on a bootstrap sample. That just means we sample with replacement from the original data. So each tree sees a slightly different version of the data set. This naturally produces slightly different kind of noisy trees, but when you average the predictions from all these slightly varied, maybe imperfect trees, it dramatically reduces the overall noise. Their individual errors tend to cancel each other out, and this leads to a much smoother, much more robust approximation of the underlying function. That's a huge advantage.
And isn't there another layer of randomness, too? To make the trees even more different from each other?
Yes, exactly. To decorrelate the trees even further. When building each tree on its bootstrap sample, you also randomize which variables the tree is even allowed to consider for splitting at each node. So maybe at one split, it can only choose from half the variables. This added layer of randomization forces the trees to explore different structures, making sure they're not all latching onto the same strong predictors in the exact same way. It prevents them from being too similar, which is really critical for that wisdom of the crowd effect to work well.
Okay, so that's random forests using an ensemble, a crowd of diverse trees. What about boosted trees? How are they different? They also sound like they involve building multiple trees.
They do involve multiple trees, but boosted trees take a fundamentally different approach. It's based on an idea called recursive fitting. Instead of growing trees in parallel, like random forests, boosting is sequential. It's iterative. You start by fitting a simple prediction rule, usually a very simple tree. Then you look at the residuals, basically, the errors or the unexplained part of the outcome from that first rule. And then you fit another simple prediction rule specifically to those residuals.
Okay. So it's learning from its mistakes, step by step, like a student who keeps trying to fix the errors from the last attempt.
Exactly. That's a great way to think about it. You keep repeating this process. Fit a rule, calculate the new residuals, fit another rule to those residuals. The final prediction comes from summing up all these prediction rules, but each one is usually scaled by a small factor called a learning rate. It's this continuous refinement process, almost like the model is fine-tuning its understanding with each pass, focusing on the parts it got wrong before.
And what kind of simple prediction rules do they usually use as the base learners in boosted trees? Are they deep trees like in random forests?
No. Typically, they use shallow trees, trees with very few levels, maybe just one or two splits, sometimes called stumps. These shallow trees produce prediction rules with low noise, low variance. But because they're so simple, they tend to have high bias. They don't capture much complexity on their own. Boosting then helps attack that bias by iteratively adding these simple rules together, gradually reducing the overall approximation error at each step, improving the fit to the data.
Got it. And how do you actually tune these boosted trees in practice to get the best performance?
Yeah, tuning is absolutely critical, just like with other complex models. You mainly need to choose the number of boosting steps or iterations, how many of these simple trees you're going to fit. And you also need to choose the learning rate, which controls how much influence each new tree has on the overall prediction. A smaller learning rate usually means you need more steps. These parameters are typically chosen using cross-validation to avoid overfitting. It's very easy if you take too many boosting iterations for the model to just memorize your training data. And if you're actually diving into this, you'll definitely run into popular, highly optimized implementations like XGBoost, LightReBM, or CatBoost. You can think of those as the highly tuned, turbocharged engines that make boosted trees incredibly fast and effective in real-world applications.
Okay, that's a fantastic overview of the tree-based world. So trees give us this powerful, interpretable way to segment data. But there's this whole other paradigm, right, that approaches nonlinearity from a completely different angle, one often compared maybe loosely to the human brain. Let's explore neural networks. What's the basic idea there?
Right. The basic idea behind neural networks is that they are incredibly powerful tools for modeling nonlinear relationships. They do this by essentially building up a hierarchy of constructed features or transformations. They create many new regressors, which we call neurons. Each neuron takes your original input regressors, your z variables, and transforms them using some learned weights and a specific mathematical function called an activation function.
Okay, activation functions. What exactly are they doing? What's their role? Why are they so important?
Activation functions are absolutely critical. There's the things that introduce nonlinearity into the model. Without nonlinear activation functions, a neural network, no matter how many layers you stack up, would essentially just collapse back down into a linear model. It wouldn't be able to learn complex curves. It's like trying to draw, a complex landscape using only straight rulers, and you need those bends and curves that the activation functions provide to capture real-world complexity. Common examples you'll hear about are ReLU, the rectified linear unit, which is actually very simple. It just outputs the input if it's positive and 0 otherwise, or things like the sigmoid function, which squashes values into a range between 0 and 1.
So the network combines inputs with weights, applies these activation functions.
Yeah.
But how does it learn what the right weights and transformations should be? I imagine some listeners thinking, wow, that sounds incredibly complicated. Can we simplify what penalized nonlinear least squares really means?
Yeah, it learns by basically solving a penalized nonlinear least squares problem. What that means is it tries to find the specific combination of all those weights and other parameters throughout the network that minimizes the prediction error, usually the squared difference between the prediction and the actual outcome, much like linear regression. The penalized part is crucial, though. It adds constraint, often like a lasso L1 or ridge L2 penalty you see in regularized regression. This penalty discourages the weights from becoming too large, which is a key technique to help prevent overfitting. Now, the actual process of finding these weights, the training, is typically done using an algorithm called stochastic gradient descent, or SGD.
Stochastic gradient descent. Okay, that still sounds a bit intimidating. Can you demystify that even further? What's happening under the hood?
It's less scary than it sounds, honestly. Imagine you're trying to find the absolute lowest point in a huge, fog-covered, bumpy valley, but you can only see the ground right around your feet. SGD works by taking a small step downhill in the direction that seems to reduce the error, the loss, the most, based on the little patch of ground it can see right now. Crucially, it doesn't look at the entire valley, the whole data set at once. It does this using batches, small, random subsets of the data. And this isn't just some minor technical detail. It's actually the ingenious trick that makes training these potentially enormous neural networks feasible on massive real-world data sets. Without using batches, you might literally be waiting an eternity for your model to learn anything useful.
And when people talk about deep learning, what does the deep part actually refer to?
Deep simply means adding more layers of these neurons. So in a deep neural network, DNN, the output from one layer of neurons doesn't go straight to the final prediction. Instead, it feeds as the input into the next layer of neurons, and this process can repeat multiple times. These layered hierarchical structures turn out to be an extremely powerful way to generate very flexible functional forms. They allow the network to learn incredibly complex patterns and representations automatically from the data, layer by layer. And that's why deep learning has become so successful in such a diverse range of problems, from economics and finance to computer vision, image processing, and natural language processing, text applications.
And I heard they can even predict multiple outcomes at the same time.
Yes, that's right. It's called multitask learning. You can design deep neural networks to have multiple output heads, predicting several different outcomes simultaneously. Sometimes, by sharing the learned representations in the earlier layers across these different tasks, the network can actually perform better on all of them by leveraging shared patterns in the data.
Okay, but with all this incredible flexibility, these deep networks sound like they could be overfitting machines, right? They can just memorize the training data perfectly, but then fail miserably on new data. How do we prevent that?
That's a huge concern, and you're right, they absolutely could. That's where regularization techniques become absolutely vital. You almost never train a neural network without them. One very popular and effective method is called dropout. During the training phase, you randomly drop out, basically, temporarily set to zero some fraction of the neurons in a layer. This forces the network not to become overly reliant on any single neuron or pathway. It encourages a more robust network where the predictive power is distributed, making it generalize better.
And the other technique you hear about is early stopping. That sounds pretty self-explanatory.
It is, pretty much. With early stopping, you don't just monitor how well the network is doing on the training data, you also keep track of its performance on a separate validation set data it hasn't been trained on. You continue the training process, like SGD, only as long as the performance on that validation set is improving or staying level. The moment the performance on the validation set starts to get worse, even if the error on the training data is still going down, you stop the training process. You basically rewind to the point where validation performance was best. For you, the listener, understanding these techniques like dropout and early stopping isn't just academic. It's often the difference between building a model that looks great on paper and one that actually delivers reliable, trustworthy predictions when you use it for that crucial meeting or business decision.
Okay, so we've covered these amazing tools, trees, forests, boosted trees, neural nets, that can approximate this best prediction rule, QCT. With all this power, the obvious next question is, how well do they actually work when the rubber meets the road?
Yeah.
And what does the underlying theory promise us?
Yeah, that's the key question. The theory does tell us that these methods, when they're tuned properly, can indeed approximate GZ very well under certain conditions. For tree-based methods like random forests, theory shows they can be particularly good at handling something called non-parametric sparsity. That's basically a fancy way of saying that even if you throw hundreds or thousands of potential variables Z at the model, if the true underlying relationship only depends on a relatively small subset of those variables, trees are pretty good at identifying those important dimensions and focusing on them. This means they can converge to a good approximation much faster than if all variables were equally important. They sort of automatically figure out what matters most for the prediction. There are also theoretical results suggesting that training them in an honest way, using separate data for tree structure and prediction estimation, helps guarantee this.
That's pretty smart. What about for the deep neural networks? Is there a similar kind of theoretical backing for why they work so well, especially with high-dimensional data?
Yes, for DNNs, the theory often points towards something called structured sparsity or composition of structure. Think of it like building a complex function not from scratch, but by combining simpler functions together where each simpler function might only depend on a few inputs. It's like snapping together pre-built Lego sections instead of using individual bricks. It's more efficient. DNNs, with their layered structure, seem particularly well suited to learning these kinds of compositional functions. This allows them to achieve potentially much better approximation rates, especially in very high-dimensional settings where traditional non-parametric methods often struggle by exploiting this underlying compositional structure if it exists.
That's really fascinating. But does the theory perfectly explain everything we see in practice? Does it tell us exactly how to tune them for the best results?
Not entirely, no. That's where things get interesting. While we have these really exciting theoretical results providing insights, there are still, frankly, substantial gaps in fully understanding why these methods, particularly deep learning, perform so exceptionally well on some real-world problems. For instance, the tuning parameter settings suggested by theory often don't perfectly match the default settings or the settings that practitioners find work best empirically. So bridging that gap between theory and practice is very much an active and ongoing area of research. It's constantly evolving.
And with all this power and flexibility, we keep coming back to this core challenge: overfitting.
Exactly. It's the flip side of flexibility. The very thing that makes tree-based methods and especially neural networks so powerful also makes overfitting a very real and constant risk. This means the model learns the training data, including its noise and quirks, too well. It performs brilliantly on the data it saw during training,
But then falls flat on its face when it sees new data.
Precisely. It's like that student who memorized all the answers for the practice test but didn't actually understand the concepts, so they bombed the real exam.
So how do we trust but verify? How do we make sure our model is genuinely learning the underlying pattern, not just memorizing the training set?
The absolute cornerstone, the crucial, simple verification procedure is data splitting. You take your original data set, and before you do anything else, you randomly split it into at least two parts. One part you use for training your prediction rule, fitting the model, and the other part you hold aside completely for testing its quality. By measuring the model's performance using metrics like test mean squared error, or maybe an R-squared, calculated on that held-out test data the model has never seen before, you get a much more true, unbiased picture of how well your model is likely to generalize to new, unseen data. This is absolutely vital for any serious real-world application. You have to test it on unseen data.
Okay, let's make this concrete. Let's bring it to a real-world example to see these methods duke it out. You mentioned a case study predicting wages. What did we learn there?
Right, so in that case study, we used data from the March Current Population Survey Supplement. It had about 5,150 observations looking at log hourly wages. And we had various characteristics as predictors, things like experience, education level, industry, occupation, geography, marital status, and so on. About 51 raw regressors in total. We compared a whole range of models: simple OLS, lasso, regression trees, random forests, boosted trees, and even a basic neural network. And here's the kicker, the surprising result. A simple ordinary least squares, or OLS model, using just those raw 51 regressors, actually performed as well as, or in some cases even slightly better than, the more complex methods like random forests, boosted trees, and the basic neural net.
Whoa, hold on, that's a real head-scratcher. My first thought, and probably many listeners too, would be that the more complex, sophisticated models always win, right? Can you unpack why OLS might actually come out on top here? What's going on?
Yeah, it definitely goes against that common intuition, and it's a really powerful point, a crucial takeaway for you listening. Don't always assume you need the flashiest, most complex tool first. For many common data sets, especially maybe in social sciences, where you might have a relatively small number of observations, like the 5,000 here, and maybe a limited number of well-understood variables, a well-understood, simpler model like OLS, perhaps with some basic interactions, can be incredibly effective and reliable. Complexity isn't always better. These more advanced methods often require significantly more data and, crucially, very careful tuning of their parameters, like tree depth, learning rates, and network architecture, to truly shine. In that specific wage study, the flexible OLS, the prune tree, and the basic neural network weren't really fully tuned with extensive cross-validation, which likely contributed to why they didn't outperform the basic OLS benchmark.
Okay, so the lesson is, consider the simple stuff first, especially if your data isn't massive or super complex. But what if we do run multiple models? Is there a way to combine their strengths? Can we sort of hedge our bets and maybe get the best of all worlds?
Absolutely. And that brings us neatly to the idea of aggregation, or ensemble learning. In machine learning, this is often called stacking. The basic idea is pretty straightforward. Instead of picking just one best model, you linearly combine the predictions from multiple individual models. It's kind of like forming a committee of experts. Each model brings its own perspective, its own strengths and weaknesses, and by combining their predictions, hopefully weighted appropriately, you can get a more robust and often slightly more accurate overall prediction.
And what are the benefits of doing that? Does it usually help?
Generally, yes. Ensembles can often, maybe mildly, improve prediction performance relative to any single one of the individual learners you put into it. They also tend to be more stable. In that same wage example, when they created an ensemble of combining predictions from OLS, lasso, random forest, boosted trees, and the neural net even just using simple OLS or lasso again to find the best weights for combining them, it boosted the R-squared slightly compared to any of the individual models. So a practical takeaway for you might be, when performance is critical and you've tried several good models, building an ensemble by averaging or combining their predictions can often give you that little extra edge and increase the stability of your results.
And now there are even automated ways to do this, right? Tools that take a lot of the manual work out of trying different models and combining them.
Yes, exactly. That's a really exciting trend in the field. These automated machine learning or AutoML frameworks, you might hear names like H2O.ai or AutoGluon. These frameworks can automatically train and tune a whole range of different models and then often build ensembles of the best ones, all within a specified time budget and often with minimal human input needed. We actually tried H2O on the wage data for that study. We gave it a time budget of just 100 seconds, told it the outcome variable and the basic control variables, and it came back with a stacked ensemble model that performed very similarly to the simple OLS, getting an R-squared of 0.287. So these tools can be incredibly powerful for quickly getting a strong duckline model or even a top-performing model, especially if you're under a tight deadline or don't have deep expertise in tuning every single algorithm yourself.
It's amazing. Technology really helping there. But I have to say that wage example still leaves me with a bit of a pessimistic impression for deep learning specifically. If OLS can beat it on that kind of data, when do neural networks truly win? When do they become the undisputed champion predictor?
That's a fair point. The wage example is definitely a specific scenario, relatively small sample size, structured, tabular data, with fairly well understood features. Neural networks, especially deep neural networks, truly win and show their power in data-rich settings. Think large samples, maybe millions or even billions of observations, and crucially rich features, especially when those features are complex and unstructured, like raw text, images, or audio. They really thrive when there's an absolute abundance of high-dimensional data that traditional methods often struggle to even process directly, let alone extract meaningful patterns from.
Okay, can you give us a really compelling example of that kind of data, where NNs just blow everything else out of the water?
Yeah, a fantastic example comes from predicting product prices, what economists call hedonic prices, using not just standard features like brand or category, but also the actual text descriptions and images of the products. Imagine you have millions of product listings from a huge e-commerce platform like Amazon or eBay. In these situations, you first use powerful pre-trained neural networks models like BERT for processing the text descriptions, and maybe something like ResNet 50 for processing the images. These initial NNs don't predict the price directly. Instead, they convert the complex, unstructured text and image data into high-dimensional numerical vectors, often thousands of numbers called embeddings. These embeddings capture the semantic meaning and visual features. Then, these embeddings, these thousands of numerical features, are fed as inputs into another deep neural network, which is trained specifically to predict the final product price based on these rich representations.
Okay, wow. And how do the results compare in that kind of setting, when you're dealing with millions of observations and using NNs to process text and images first?
The results are dramatic. It's night and day compared to the wage example. When you use deep neural networks on these rich text and image embeddings, you can achieve R-squared values for price prediction that are around 90%. Extremely accurate. In contrast, if you try using, say, a random forest on those same embeddings, you might only get an R-squared of about 80%. Still good, but a significant drop if you use just a linear model on those embeddings, maybe 70%. And if you completely ignore the neural network embeddings and just try to predict price using simple catalog features like brand, category, etc., the R-squared might plummet to below 40%. This perfectly showcases where NNs excel, extracting powerful, abstract, predictive representations from massive amounts of high-dimensional, unstructured data. They learn features that allow them to achieve a level of predictive power that other methods simply can't touch in those domains. That's the real aha moment for deep learning.
What a journey we've been on, starting with that great quote from Leo Breiman about no stone tablets. Then working through the elegant simplicity perhaps of regression trees, the ensemble power of random forests and boosted trees, and then landing on the brain-inspired complexity and incredible power of deep neural networks. It's really clear these are all just different powerful tools aiming for the same goal, approximating that best prediction rule, that GEZ.
Indeed. And we've seen how they work mechanically, right? The splitting, the averaging, the boosting, the neurons and layers. We touched on the theoretical insights behind why they might work so well, handling sparsity, exploiting compositional structure, and we've repeatedly emphasized that crucial need for validation, for data splitting, to guard against that ever-present danger of overfitting. The wage example was a great reminder that sometimes simpler models can be surprisingly effective, especially with limited data, and they should absolutely always be in your toolkit, always considered.
Absolutely. But then that hedonic pricing case just vividly illustrates where the true, maybe unique power of deep neural networks really shines.
Yeah.
In those data-rich, high-dimensional scenarios, where they can extract incredible insights from really complex features like raw text and images. So the big takeaway seems to be, there's no single best model, is there? The choice really always depends on the specific data you have at hand and the particular problem you're trying to solve.
No, there really isn't. And that's precisely why this field is so dynamic and, frankly, so exciting to work in and follow. The landscape is always shifting.
And it really leaves us, and hopefully you listening, with a provocative thought to mull over. What fascinating new ways might we discover next to combine these different methods? Or maybe what new theoretical understandings are just around the corner that could unlock even more predictive power from these tools? The exploration, it seems, never really stops.